All right, yeah, thank you very much for the invitation, and thanks to the organizers for organizing this very interesting workshop. Today I will talk about how we can use machine learning for estimating thermodynamic observables in lattice field theories. And this is some work done in collaboration with all of these people here. This is published here, so if you want to see more information, feel free to read the paper or drop me an email. The first thing I would like to emphasize is that the main part of this work was done by Kim, who is a PhD student at the Technical University of Berlin. And Kim, Christopher, Pan, and Shin, they are members of the machine learning group at TU Berlin. Tobias is a mathematician, Carl and Paolo are mostly working on lattice gauge theory, and I myself have a particle physics and lattice gauge theory background. So we have many different various research backgrounds within our collaboration. So to start with a very broad overview, why we want to use machine learning for thermodynamic observables in lattice field theories, one can draw this very simple picture that in physics we have experiments, theories, and then numerical computations for regimes of parameter spaces where we can't have analytical computations. And in particular, lattice gauge theory is a very successful example of numerical computations in particle physics, where we have reached an era of high precision computations after several decades of research. However, there are still some computational issues, which was discussed at this workshop yesterday and today already. And there are several different avenues to tackle these computational issues. And so 3 of these possible avenues that have been proposed are tensor networks, quantum computing, and machine learning, where they try to tackle different problems. For example, tensor networks and quantum computing try to tackle the sign problem of lattice QCD that enable to simulate something like topological theta terms or chemical potentials, where in machine learning, we have many different applications, including efficient sampling, which was mentioned by Daniela yesterday, and the estimation of thermodynamic observables, which is something I would like to talk about today. So what kind of models are we looking at? So the real world, of course, is 3 + 1 dimensional QCD and Higgs theory and electroweak theory of the standard model of particle physics with real quarks, real gluons, real Higgs particles. However, these new avenues to tackle computational issues of lattice QCD, many of them focus at the moment still on 1 + 1 dimensional models. For example, there's the Schwinger model, which is a toy model for QCD that also contains a theta term and confinement. One can add a chemical potential. This is a famous benchmark model for tensor networks and quantum computing applications. And today in my talk for machine learning, I would like to talk about 1 + 1 dimensional phi⁴ theory, which is a toy model of the Higgs theory of the standard model, where we have phenomena like symmetry breaking, generation of a vacuum expectation value. But you've already heard by Daniela yesterday that one can also look at more complicated theories, including fermions and also including, for example, SUN gauge theories, which will be addressed by Gurtej Kanwar on Thursday in his talk. So what kind of observables are we interested in? Today in my talk, I would like to talk about the free energy and the entropy and pressure that can be derived from that. And these are observables that for lattice QCD are very important in experiments and observations at LHC and in cosmology, in particular for heavy ion collisions that are currently studied at the Alice experiment at LHC, where one is simulating the physics of the early universe right after the Big Bang at very high temperatures. So you've already heard in several talks that lattice QCD, and in particular the main ingredient MCMC, has several computational issues. And just as a reminder, the goal is that we want to compute observables. However, we can't make this very complicated integration because of the high dimensionality of the integral, and therefore we are sampling. And so we're sampling histories in the path integral, and this is the path integral distribution, p phi, which is simply the exponent of minus the action divided by the partition function. And now MCMC, as you know, simply means Monte Carlo. We're drawing samples from the distribution p phi, the path integral distribution, Markov chain means the next sample is depending on the existent one. And we have several problems with this approach, in particular, critical slowing down. It's computationally very hard to tackle phase transitions. We have autocorrelations with MCMC. And one thing I would like to talk about today is that we don't have any direct access to this partition function Z. So for example, in Lattice QCD here, that's a plot, we would like to compute the pressure, which is capital P here, as a function of the temperature. And we unfortunately don't have any direct access to the partition function Z, and therefore to the free energy F, which is given by minus the temperature of the log of Z, and which is equal to minus the pressure times the volume of the system. So if we want to compute with Lattice QCD computations, the pressure, which are the black and the green data points here, where the blue region here is a perturbative high temperature computation. If we want to compute this pressure, we need to have an analytical starting point, an approximate or analytically well-known starting point of our MCMC computation, and then we're integrating through phase space. So we have a reweighting procedure to get to observables at higher temperatures, and this is in particular challenging if we are crossing a phase transition, as in the QCD case where we have the deconfinement phase transition here. So with this integration through phase space, we get large statistical errors, and this is one of the main goals that we are trying to tackle with our work. So as I mentioned, the state of the art is that we have the critical slowing down. We don't have any direct access to the partition function Z. And I will later in detail explain what exactly the problem is and how we address this, usually with MCMC. So now one proposed way to overcome problem of autocorrelation is to use a flow Q theta of phi, which was introduced yesterday by Daniele Rezende here, who's one of the authors of these papers that propose to use the flow to approximate the path integral distribution. Another author, Gortej Kanwar, will talk on Thursday about applications to SUN theories, while in my talk today, I will only talk about the scalar phi to the 4th theory. So the reason now, the method now is to take the flow and to optimize it with respect to the parameters theta of the flow. Then one can very efficiently sample from Q theta of phi in a highly parallelized way, and one can generate uncorrelated configurations. And this is something that was discussed already on Monday, will be discussed in more detail on Thursday. And what I will discuss about today is that we used this approach to compute thermodynamic observables by training the flow and sampling from it. So we're computing the free energy F given by the log of Z that we don't initially know, by training a flow and sampling from it. And therefore we can estimate observables that are not directly accessible with MCMC. And this is the final plot that I will explain to you in more detail later in my talk. So to set the scene, the starting point are deep neural networks. You already have heard a lot about them, but I want to introduce them again to focus on the symmetry parts of our phi to the 4 scalar theory. First, we have the layers YL, where we have an input X, the output is YL, and we have several parameters, the weights W and the bias B. The bias has to be set to 0 because in our phi to the 4 theory, we have a Z2 symmetry. So the action of the theory is invariant under changing phi to minus phi. At the same time, we're choosing an activation function, which is a tangents hyperbolicus of X due to the same reason, due to the Z2 symmetry, because it means that we take tangents of minus X, we get minus tangents of X. And therefore we see that our network is actually equivariant with respect to the symmetry. And this difference between equivariance and invariance, this was already discussed yesterday by Daniela. So on the level of the network, our network looks simply like that. We have these different layers, YL, L minus 1 to 1 applied to X. And this network is odd, as I mentioned above. So if we apply G theta to minus X, this is equivalent of having minus g theta of x. So we have equivariance here, which is due to the invariance of the action with respect to the Z2 symmetry. And usually people call a neural network deep if the number of layers is around 10 or larger, but this is not a hard cutoff, it's just a rough estimate. All right, let's look now at normalizing flows that were also already introduced yesterday. We know that generative models are built from neural networks, and normalizing flows are a subclass of generative models. The input that we're choosing in our case as the prior distribution is simply a normal distribution. And you see directly it's respecting the Z2 symmetry. Then we have the neural network, which we had on the previous slide. And the individual coupling layers then are applied to the sample Z that we're sampling from this initial prior distribution. And then after training, we get the final output distribution, which can be some complicated distribution Q theta. And you also saw this formula already yesterday. This final distribution is given by QZ of the inverse of that neural network, and then the inverse of the Jacobian determinant. And then when we're sampling from that final distribution, this is equivalent to sampling from the initial distribution QZ and applying the neural network G theta of Z to the sample Z. So let's look at the technical details of the machine learning architecture that we're looking at. The architecture is called Nonlinear Independent Component Estimation, or NICE architecture. And here's an image from the original paper that proposed the NICE architecture, where they trained the model on the Toronto face data set. And this is these are the generated images from there. And if you now look at the final distribution that we get using the NICE architecture, we see that we have two requirements on the architecture. And these are requirements that were briefly already discussed yesterday, namely that the neural network has to be invertible and the Jacobian determinant has to be efficiently evaluable. And this is done in the following way. So we're splitting the layers into YU and YD, also similar to yesterday with this checkerboard pattern where the next layer has an alternating checkerboard pattern compared to the previous layer. And then we are imposing this recursive definition of YU and YD. So YU L plus 1 is simply equal to YU L, which is equivalent to what we saw yesterday. But for YD, we have a difference for our NICE architecture. Here, YD L plus 1 is given by YDL plus the neural network M that I will talk a little bit more about later. So we see directly that this results in an invertible neural network. This is simply the inversion. And then we see that the determinant is very efficiently evaluable. It's completely trivial. So you already saw yesterday this trick that by splitting the layers and having YU L plus 1 equal to YUL is giving a zero component up here in the determinant such that the off-diagonal contribution to the determinant is vanishing. And now on the diagonal contribution, we have two identities, and this is different to what you saw yesterday. There we just had one identity here, something more complicated down there, but here we have two identities because that neural network M only depends on the YU and not the YD of the L layer. So you see automatically that the requirement that the Jacobian determinant has to be efficiently evaluable is given because it's equal to 1 and therefore it is trivial. So this is a very, very simple architecture for machine learning. Regarding these parameters, the neural network M contains the learnable parameters theta of the flow G theta of Z. And regarding the number of layers, G has 6 coupling layers and M has 5 hidden layers. So therefore the network is actually deep enough to be called deep. So now I would like to talk about how we approximate the path integral distribution. And the target distribution, as I mentioned in the beginning, is simply the path integral distribution P phi, which is given by 1 over Z exponent minus the action. And now we want to train the flow such that it is as close as possible to P of phi. And the way how we do the training is we're minimizing the KL divergence between Q theta and P, something like that you already saw yesterday as well, that we have the log of Q theta and P. So this log is vanishing if q theta is equal to p, and that is the minimum of the KL divergence at simply 0. So in our case, as I mentioned in the beginning, we're interested in free energies. So we have two free energies here, FQ and F. FQ is the variational free energy. It's simply given by the expectation value where we're sampling from q theta, from the train distribution, the final train distribution. And we have the action S of phi and the log of q theta. And the free energy, the true free energy, the F here, is simply given by minus the log of Z. And this is something you can directly see when you plug in this expression for P of phi here into the log. You see that this second term here of the variation of free energy is simply the numerator. And for the denominator here, we have S of phi from up here. And we get minus ln Z from this normalization prefactor 1 over Z in our target distribution. So now you see that the KL divergence is minimal. It's equal to 0 if F is equal to FQ, which means that the variational free energy that we obtained from training our flow and sampling from our flow is resembling the free true energy that we're actually interested in computing for the phi to the 4 theory. And one last thing to mention here is that the temperature, just as yesterday, was defined here as the inverse beta inverse A times NT, where NT is the spatial extent of our lattice and A is the lattice spacing. And we have a two-dimensional lattice in our phi to the 4 theory. So the trick that we're using now is a trick that I already mentioned implicitly, namely that the KL divergence is larger or equal to 0. And this is due to the Gibbs inequality, and it means that it's actually sufficient to minimize the variational free energy FQ. So it's actually not relevant what the normalization factor of our target distribution is. So F is irrelevant, we can neglect it, because the free parameters of the KL divergence, they're only contained in FQ, in the variational free energy, while the target F is independent of those parameters. So what we then can do, using gradient descent with respect to theta, we can obtain the value of Q that is as close as possible to the true value F. And this is exactly the same expression that I had on the previous slide, simply the action plus the log of Q theta. And this can be called the unnormalized importance weight minus the log of this unnormalized importance weight W tilde, and that's simply defined by exponent minus the action divided by the flow, the Q theta distribution that we obtained after training. So now the way how we're sampling, we can write the approximated partition function Z that we obtain now after training. We can write it like this. That's very simple to see. When you plug in this unnormalized importance weight into here, you see that Q theta and Q theta here are canceling out. So you simply have integration over d phi exponent minus the action, which is the partition function. And what we can then do so this is the way how we're training. Now let me introduce the model to you, phi to the 4 real scalar field theory. So the action we're looking at is precisely this one. Yesterday you saw a different action. It looked different, but it's actually the same. It's where the potential is written as m squared phi squared plus g phi to the 4. This is just a different rewriting of the action, but it's basically the same. So just a different parameterization where kappa is the hopping factor, the hopping parameter. That's what it's called. And lambda is the coupling of the theory. So this action is invariant under Z2 transformations, as I mentioned before. So we can go from phi to minus phi, the action stays the same. And therefore we have to choose a flow that's equivariant with respect to the symmetry. Now, what kind of observables are we interested in? First of all, the absolute magnetization, which is plotted here on the right-hand side. And the second observable, the most important one, is the free energy, which is given by minus the temperature, the log of the partition function, and that's equal to minus the pressure times the volume of our simulation. So what you now see here on the right-hand side is that we have a phase transition. We have spontaneous symmetry breaking. When we are keeping lambda fixed, we keep it at 0.022. And then we're scanning through kappa from 0 to 0.5. You see that we have a phase transition here at this point between 0.2 and 0.3 in kappa. So we have different lattice sizes here, and T is the temporal extent of the lattice, and X is the spatial extent of the lattice, where we used different ones in our simulation. And you see that you have a point here, kappa equal 0.3, which is the dashed line, where we are actually beyond the phase transition. And this is now where our main interest is lying, exactly at this point, kappa equal 0.3, because this point is very hard to reach using Markov chain Monte Carlo techniques. And this is something I would like to discuss on the next slides. What is really the issue with MCMC, how to compute this, and how we can overcome this with using the flow. So the critical problem here is that we don't have a direct estimate of the partition function Z, and therefore of the free energy, which is minus T of ln Z. And the reason is that we can only estimate differences of the free energy with MCMC. So if we have some target free energy Ft, which could be here at the point kappa equal 0.3, and we have some initial free energy F0, then we can only compute the differences between those two. So F0 could be, for example, at kappa equal 0.0. Now this difference is given by minus the temperature and then the log of Zt over Z0, where this is simply given by the expectation with respect to the exponent minus St over the exponent minus S0. So you see that with MCMC computations, if you want to compute Zt, some kind of partition function at the target point in parameter space, you can only do this with respect to a reference point Z0. So this is what you can compute, and then you multiply it with Z0 in order to get Zt. But it's not possible to directly go to your point in parameter space and make your computation there. So we need to have a trajectory. And in our phi to the 4 case here on the right-hand side, the starting point that we choose is at kappa equal to 0 down here, because at this point, we know that the free energy F is known analytically. We can actually solve the integral and get a result depending on Bessel functions and so on. And there's no systematic error whatsoever, while for lattice QCD computations, the starting point actually has some kind of systematical error, which I will talk about later. Now the target point is beyond the phase transition in our study. So at kappa equal 0.3, and when we now want to reach this target point, we have to pass through the phase transition. And this is the main problem now, because the variance of this estimator here, Zt over Z0, this is increasing for decreasing overlap of P0 and Pt. So the probability distributions for our path integrals at these two specific points in parameter space. And when we're passing the critical regions, those will be more and more peaked. So the overlap will be smaller and smaller. And therefore, when we want to go from here to there, the path integral distributions will look very differently. And we can't simply take this very simple approach here that we take Ft minus F0 and try to compute this with MCMC. Instead, we have to take several different steps. So the step sizes that we're using here is that we have a size of 0.05 when going from 0 to 0.05 and so on. And in this critical region, we're refining the step size further and choose a step size of 0.01. Because as I mentioned before, when we're exactly in the critical regime here, the correlation length is increasing, and then we need to make a smaller step size in order to have sufficient overlap of the probability distributions for the different steps in our Markov chain. So that means we're integrating through phase space, and this is giving us large statistical errors. And this is exactly what I mentioned in the beginning in the motivation, that if we are looking, for example, here at the lattice QCD plot, where we want to compute some thermodynamic observable like the pressure at high temperatures, then here we are in the deconfined phase of the theory, and here we are in the confined phase of the theory. Here we have a phase transition, so we're passing through that phase transition. And the analytical starting point for computing the high energy observable is in the confined phase. And while we're passing through that phase transition, we get exactly that problem that we have to take a smaller and smaller step size when approaching the transition, and this will give us our statistical errors. So in the following, I would like to compare the MCMC and the flow results for our phi to the 4th theory study in 1+1 dimensions, first before the critical point and afterwards after the critical point, so that you can see the difference, the conceptual difference between passing the phase transition and simply staying at one side of the phase. So the parameters before the critical point are kappa equal to 0.05. The lambda parameter is the same as before. So if we go back, you see that this is here, this region. So 0.2 is before the transition. We're looking again at different volumes. So this is the x-axis here. We have different lattice sizes. And for the MCMC, we use standard hybrid Monte Carlo algorithm, but I have to emphasize here, we use a very inefficient implementation. We have a Python implementation instead of C, and one could heavily optimize the HMC. One could also heavily optimize the flow. Also on the flow side, we use a very, very simple architecture. So when you look at the error bars and like the hours it takes to generate the data, that's something that shouldn't be taken too seriously. It's just a matter of a proof of concept demonstration of what happens when we pass critical points when computing thermodynamic observables. But both of these approaches can be highly optimized. So the error bars can shrink, the runtimes can get reduced. That's something one has to emphasize here. So in this HMC algorithm, when we're before the critical point, we have 4 Markov chains when we go from F0 to Ft, because we have these step sizes of 0.05. For the flow, we have the Z2 symmetry incorporated into the flow, as I mentioned in the beginning. And here, unlike for the MCMC, there's no starting point needed. So we can directly go to the desired point in parameter space, so we don't have this integration through phase space. But what you see here, that before the critical point, you see the error bars are kind of comparable. They're very similar to each other. And this is now different to the case when we're passing the phase transition and we're after the critical point. This is the next thing I would like to show you. So here we're increasing kappa. So now we have passed through the phase transition, and you see that the errors are getting much larger from the HMC simulations, while for the flows, they still stay relatively small. So now you see for MCMC, we have 14 Markov chains instead of 4, because we had to take these small step sizes when we go through the critical point. And we're crossing the critical region, and that's the reason why we have larger errors, as I mentioned before. So for the flow, the error bars are similar as before. And so the precision is, it's not that dependent on the point in parameter space. So we can go to any point. Of course, when we're exactly at the critical point, training will be harder and so on. But we always trained until convergence. So then the resulting error that's coming is only coming from the bias, for example. These are errors I will discuss later in the talk. So this is the main take-home message when we compare before and after the critical point, that one conceptual advantage of flows on top of all the advantages that are discussed at this workshop, one conceptual advantage could be that if we want to compute a thermodynamic observable where for MCMC we had to cross the critical region, for the flow we don't, and we can go directly to the point in parameter space, which is reducing the errors. So let us compare now the errors for MCMC. So we see on the one hand that the error is increasing with the step size, so we can reduce it by taking finer step sizes. That's one thing we investigated. However, at the same time, the integrated autocorrelation time is increasing when we're decreasing the step size. That's what you see on the left-hand side. And what you see very nicely in this plot here on the left-hand side is that in the critical region, which is highlighted here in red, you see that here the integrated autocorrelation time is peaking. So this is exactly what you are expecting from MCMC computations. Now we can come back to this previous plot I showed from the Lattice QCD paper from 2016, that we have an additional error if the starting point for the free energy is only approximated. So in the phi to the fourth theory in our paper, F0 is exactly known, so we don't have any additional error there. But in finite temperature QCD, this F0 starting point is chosen usually from, for example, the hadron resonance model, where we have only an approximative value for F0. So this is introducing an additional systematic error for the MCMC side. On the side of the flow, we also have systematic errors. And for that, just to give you a brief reminder, what we're actually computing, we're computing the KL divergence, which was the difference between this variational free energy FQ and the real free energy F. So now the question is, how far off are we? This is something which was discussed in the previous talk, the problem of a bias. And we are monitoring how strong our bias is by looking at the variance of a variable called C, not Q. And C is basically beta times FQ. So beta, the inverse temperature times the variational free energy. That's how we define it. So it's simply the logarithm of that unnormalized importance weight that I discussed previously. And it can be shown that the KL divergence is equal to 1/2 of the variance of this observable C plus some higher order corrections that are depending on the importance weight W, which is normalized, so Q theta over P. So if we have a perfect training, then the KL divergence vanishes. Then Q theta would be equal to P, and we would have a perfect approximation of the path integral distribution. However, we don't see this when we're training. So we're starting here, then we reach convergence after around 10 to the 5 training steps, but we're not converging to 0. We instead converge to a value of around 1/2. And so we see that this is introducing a bias into the computation due to that imperfect training. But the good thing here is that one can show that the bias is scaling like 1/n, and this is a subleading error compared to the error of the estimator itself. So when we compute the free energy, as I mentioned before, what we're doing is we take the log of the partition function, and this is given by sampling. We're sampling from the target distribution, the phi i's, and then we take this unnormalized importance weight, which is precisely that expression I defined here and previously. And one can show that this standard deviation is falling off like 1/√n, which is the standard Monte Carlo scaling. So you see that the error of this estimator is actually dominant compared to the bias due to the imperfect training. So the last thing I would like to discuss are the computational costs, because we had this in the discussion yesterday. I wanted to comment on that now as well briefly, that for the MCMC, of course, we don't need any training, but we have sequential sampling. And therefore, we have large sampling costs if we have a large number of samples. For the flow, the situation is the opposite. We have an upfront training cost. In our case, it was around 20 hours. So it's a constant upfront training cost. And then the sampling can be highly parallelized. So in our case, we had 5.6 million samples, and we could generate them in less than a minute. So the sampling is effectively coming for free, but the training is very expensive. So you see then these two lines here. And the question one is now naturally asking is, when can the machine learning algorithm beat MCMC, if it can beat it at all? And so this question has many different answers. And of course, the first answer would be, it depends on what you're actually looking at. So as I mentioned in my talk, that when you look at thermodynamic observables, and for the MCMC, you have to pass the critical region. This is a point where one has some conceptual advantage from the machine learning approach, where machine learning could help to beat MCMC earlier. On top of this advantage that was mentioned already yesterday in Daniela's talk, that we have this very efficient sampling, and therefore we could reach this crossing here of training, whereas the sampling costs independently of crossing these critical points. But this is an additional advantage of the flow. And then one, of course, has to optimize everything further. So in our case, we used a very simple architecture for the flow, and we haven't tuned any hyperparameters or anything. And of course, one has to further optimize the architecture, like we discussed yesterday. To really reach lattice QCD, one has to include the fermions, one has to include gauge fields, as will be discussed on Thursday. One has to go to larger lattices, one has to go to higher dimensions. And especially the aspect of larger lattices is an issue for the training, because currently the training costs are scaling exponentially, but it's hoped that better machine learning architectures will be able to overcome this issue such that we only have a polynomial scaling there. Yeah, so I think one can say, because Lattice QCD was in the very early stages in the 1980s, also looking only at very small systems. And today we see, after several decades of research, that we've reached very high precision computations that, yeah, maybe machine learning for lattice field theories will have a similar path, and we will have it as a standard computational technique as part of Lattice QCD in maybe a couple of decades. So this brings me to my summary. And yeah, the motivation was that for MCMC, we have the critical slowing down. And in particular, we don't have any direct access to the partition function Z. And so it was proposed, for example, as discussed in the talk by Danilo Resende yesterday and Gortet on Thursday, that one can train a flow to approximate the path integral distribution. And we showed that this can be used to compute thermodynamic observables, such as the free energy, with first training the flow and then sampling from it. So we can estimate thermodynamic observables that are not directly accessible with MCMC, where we can only have the differences of free energies and of the partition function. And so therefore, we don't have any integration through parameter space that's required. So this is particularly relevant when we're passing critical points and when we have a starting point of our MCMC computation where we have an additional statistical, systematic error connected to the starting point. So in the future, as I mentioned, we have to look at extensions like larger lattices, gauge fields, fermions, higher dimensions. And all of this is needed for the long-term goal to be able to incorporate this to lattice QCD calculations at high temperatures, for example, the ones that are studied at the LS experiment at CERN. So that brings me to the end of my talk. Thank you very much for listening. And if you have any questions, feel free to ask them now or drop me an email later if you want. Thank you.
Thank you very much, Lena, for a very nice talk. Yes, please. So I'm going to hand it over to Gerrit Arts, who's our discussion leader now, since this might just sort of blend into the discussion session. But if you have questions for Lena on her talk, please use the raise hand button. And Gerrit, if you look at the participant list, you'll see the list of people with their hands up. So go ahead, Gerrit.
Okay, thanks. Thanks a lot. Yeah, so we'll start with questions about this talk. George?
Thank you for the talk. I think for the numerical comparison of the cost, wouldn't it be better to use the most efficient MCMC algorithm we have, which is not a hybrid Monte Carlo, but using the cluster algorithm? And so, I mean, one thing I'd be very interested to know is, does the machine learning architecture learn about clusters and the embedded clusters, and does it learn how to efficiently generate lattices based on using clusters? Because we know using cluster algorithm, we can generate configurations with essentially zero autocorrelation time. And also, I think that there's, once you have access to clusters, there are also, Hasenbusch has shown that there's ways to get access to the partition function by playing this game of comparing whether you can generate configurations with periodic and anti-periodic boundary conditions using clusters. And so that you can also directly access the information about the partition function that way, or at least the ratio of the partition function with different boundary conditions. So it might be to really answer this question of whether your machine learning is a win, you should try to use like the best algorithms and the best observables we have. So,
yeah, that's a very good comment. So what we did was we used also on the machine learning side a very, very simple one. So this could also be optimized in our comparison. So you're right, one has to compare it with way more efficient. Let me go back to this issue here. So so you're basically saying that yeah, if we don't use HMC, we could actually access these points in parameter space directly without actually starting from F0, such that we integrate through this critical region. That's
yeah,
what you mean with the cluster
algorithm in particular works best at the critical region because that's when the clusters are largest. So actually you have this problem with the embedded cluster algorithm that very far away from the critical region when the correlation length is very short, it's almost like Metropolis or hybrid Monte Carlo. But in the critical region, when the clusters grow to be the size of the lattice, then the cluster algorithm is extremely efficient because you're basically changing all the spins at once. So with an order volume operation. So and in an uncorrelated way. So I mean, it's very, very beautiful actually.
Okay, yeah, thanks. We have to look into that. Yeah. So we actually at the moment, because that's a conceptual problem, then for the specific for the HMC, that's the matter of comparison we used here. But yeah.
I mean, I agree with Tom's point that there's no cluster algorithm for QCD that we know of yet. But the idea would be
that explains why
the machine learning can match a cluster algorithm in an example where we know that there's a cluster algorithm, then maybe we can use what we learn from machine learning to find some better algorithm for QCD.
Yeah, and also then for the cluster algorithm, I mean, it's then two different algorithms tackling the same issue, and then one could see whether like which one could be developed more quickly in order to actually reach QCD in 3 possible dimensions. Yeah, that's true. But,
thank you.
Thanks.
With respect to this plot here, I mean, the problem in QCD also to go to very high temperature is to maintain a good aspect ratio and have n tau not too small, have it feasible to run on a computer. So it's not only the integration through from small, it's also to have lattice spacing and aspect ratio and volumes all being accessible. Okay, Gorte, next question.
Thanks. Yeah, I appreciate the talk, Lena. Very interesting results. The one thing that caught my eye, I guess, was this bias that you talked about in the estimator of log z. And I wonder if you had compared this estimator where you take the average of the log reweighting factors versus the average of the reweighting factors themselves, no logarithm, which would give you an unbiased estimator of z, and then applying the log outside, which maybe reintroduces some bias at finite sample size, but might have a different bias variance trade-off. So have you explored that estimator at all in comparison? And have you found one to be better or worse than the other?
No, we have this was the only one we looked at, and it was we always like check that one to reach that convergence level around here. So would you expect to have a different outcome if you use the different bias estimator?
So at least in our applications to the gauge theory results that we've been working with, we found that the estimator where you apply the log outside tends to be far more precise and less biased, even earlier in training. So it might be worth comparing if you haven't taken a look yet.
Okay, yeah, that's.
I'm not sure if it applies in this particular example as well. But.
Yeah, okay. Yeah, we'll have a look at that. Thanks.
Thanks.
Gergo?
Yep. Thank you for the great talk. I enjoyed it a lot. So my question is about in the integral method, when you do the usual way of calculating the pressure there, so looking at differences of free energies or pressures is One thing it helps with is that you can express it via an integral, but the other thing is that it also the additive divergence is cancelled, right? So I'm somehow wondering, where do these additive divergences disappear in this discussion of yours? I assume that also 2D phi to the 4th theory has those additive divergences. So where are they here?
So you mean when we're sampling here from the anomalized?
No, I mean completely generally. Isn't the pressure at some fixed kappa value infinite in the continuum limit without renormalization? I would guess it is, isn't it?
But it would be quartic divergences in 4 dimensions.
Maybe it's just quadratic because it's 2-dimensional, but
no, yeah. So when you put the pressure to 0 at 0 temperature, then that's a normalization.
Yeah, but then you really choose a difference of two pressures. Then you compare to the pressure at 0 kappa, for example. But here I had the impression that you're somehow getting rid of this normalization issue. So I'm just missing the point where why does this divergence not enter?
So you mean, okay, let me go there.
For example, on this the magnetization, but I mean, so the pressure at 0 kappa is also an integral of the magnetization somehow. Shouldn't it be infinite?
And you mean, so the, like, what the free energy of the system? Let me, yeah, I have to think about it. I didn't think about that. Yeah. I mean, you mean, so, okay, in here you have the same divergence factor and that would cancel out originally, and it doesn't cancel out.
Yeah, that's what I mean.
Yeah, this is actually true. Well, I have to think about it. Yeah, I will come back to you.
Maybe if I have a very short follow-up. More, I think one more page to the right, where you have this KL divergence that you said is not depending on F. Can you?
I know. So you mean the other direction? So. Yeah.
Somewhere there.
You mean that?
That
yes.
Minimizing is sufficient. I didn't get that. How come it has to be positive if it's a difference of two free energies? Can't be F smaller than FQ, or the other way around? Why is this positive definitely?
Yeah, so that's due to the Gibbs inequality. I have a backup on this. So because the KL divergence is so if you look at the definition of the KL divergence and the logs, that basically means you have in the KL divergence P log P and P log Q, where P was your path integral distribution and Q was your trained one. And so these mixed divergences, they're always smaller or equal than the P log P1. So this is a fundamental like quantum, it's like an information theoretic inequality that, yeah, I don't have the proof here, that's true of the Gibbs inequality. But for the KL divergence, it always has to be larger or equal than 0. And then for the free energy, because one can simply reparameterize it, it automatically holds true for the for that variational free energy that we have with respect to the. So we know that the KL divergence always has to be larger or equivalent to 0, and the way how we simply rewrite it in terms of the free energy is simply rewriting it in terms of F. So there's no way to have a negative when the starting point is already positive.
Yeah. Okay. I have to think about it more. But
okay. Yeah, and thanks for your first question. I will think about it. There's something in the chat. Maybe have a look.
Did I get on the question list here? I'm not sure. I did this
right. Kim was saying something.
Oh, I was, this is Richard. I didn't know, did I get on the question list?
Raise your hand, Richard, but go ahead and ask a question. And now you do.
Yeah. Can I ask a question? Yes.
Okay, yeah.
Yeah, very, very interesting talk, by the way. I'm really fascinated. I'm wondering, in this case, we know that the phi-4 theory is in the same universality class as the Ising model, right? So we have another thing we might, maybe you've done this or other people have done it, but suppose you were doing this in the Ising model, then your initial distribution would be plus or minus 1s or plus or minus the VEV, whatever it is. And that's a very different sampling. First of all, I wonder if it worked for the Ising model. You should get the same answer. It's identical in the continuum limit.
I mean, shouldn't it be much simpler?
Well, I think it should be, but now I'm going to try to say whether I can learn from this. I mean, then you could ask yourself, if you're in the same universality class as this model, maybe you should have started in taking plus or minus something or other as your initial model, which is very different from your Gaussian input. So then I'm asking whether that would then inform you on how to get to this critical property.
But if it's simply, I mean, if it's here much more complicated, the phi, wait a moment. So, I mean, our distribution is much more complicated than simply the plus and minus for the,
well, I mean,
model, right?
it really, no, it really, no, it really isn't. That's the point of universality. I mean, you can do the cluster algorithm for phi-4 theory, and basically it has clusters and it flips a sign. And then there's small oscillations around those clusters, which represent the phi, if you like, the Higgs not being frozen. So I mean, it's really the same theory. I mean, maybe go back to George's thing. Suppose you had a random cluster model that was completely soluble. So you could then start with a correlation line in the random cluster model that was just tuned to be where you want to be in the plane of the phi-4 theory. If you can solve that random cluster model, then you could start it. That is your initial conditions. And what you're doing is you're sampling closer to the target in
actually,
infrared sense, right?
Yeah.
That's what you want to get is to the infrared physics.
Yeah. So I don't know if you can see the screen here, the paper. So Kim, like one of my collaborators, he just posted into the chat this paper that he wrote in collaboration with Shin and Pan, like my other collaborators, and they actually looked at the 2D Ising model. So maybe Kim wants to say something about this. I wasn't actually aware that they looked at the Ising model. So
what I want to use is the Ising model as a way to inform how to do this model. Okay.
Yeah. So sorry. Hi, Lena, and thanks for the very nice talk. Just to comment a little bit on this, we had, this was our previous work where we used a slightly different architecture with our autoregressive network, which one can see essentially as a discretized version of the flow, which is maybe not perfectly correct, but at least it gives a feeling. And we use them to study the 2D Ising model as a time model, and we showed basically how one can get unbiased estimators, and like Lena previously shown for the phi-4 theory, we also derived quantities which cannot be accessed by a standard MCMC. But getting to the topic of clusters, there is a recent work from Carleo and collaborators, which I also posted in the chat, where they essentially analyzes same, I think, two setups. One is the 2D Ising model as well, and they showed how incorporating, doing a cluster updates using similar techniques rather than global updates does help to escape local minima in the MCMC sampling technique. And they also do some other additional tricks like incorporating symmetries and stuff like that. So I think this might at least partially answer your question on that.
I see. Yeah, that's very interesting. I mean, my point is this, that cluster algorithms are probably hopeless in gauge theories as an exact algorithm. But a cluster is a concept of collective variables. So you might have a cluster approximation to the vacuum that you're looking at, which you then use as the starting point for machine learning. And then the machine learning would be correcting your inability to define an actual cluster algorithm. And that would then open up cluster algorithms as an approximation scheme with then an unbiased estimate, which would be a really very significant development, I think.
Do they look at this here, Kim? Do they, or was that not explored? Do you know that?
I
haven't read this paper.
No, I think they didn't explore this. So their main contribution is that they rather than doing global updates as we were doing our previous work, they do cluster updates. So they randomly select the number of splints configuration that get flipped at each step. And this basically allows you to reach ergodicity, which was not, from which we were prevented from our previous work because there was still not enforced ergodicity from our previous unbiased estimator. And then what they do, they also incorporate the symmetry. I think it's a Z2 times Z2 times Z2 symmetry in the second model that they analyze, and the Z2 invariance in the 2D Ising model. I think they present this in the, this FPM frustrated plaquette model, which is slightly more complicated than the standard Ising model. And so I think we're not yet there, but I found this a very nice starting point to, I mean, we saw how cluster algorithm improved upon standard Monte Carlo, at least in the early 80s or whatever. And I think being able to apply a similar kind of machinery, also combining this with machine learning, might lead to some nice improvement in that.
Yeah, I mean, you are aware that the cluster algorithm applies to 5-4 theory just as well as the Ising model, right?
Yeah, I said that already.
Yeah, okay.
But to me, the thing that I'm worried about is in an autoregressive model, if you take the cluster algorithm and do a bunch of cluster flips and then show it to the neural network, I'm sure it would eventually pick up on the fact that clusters are really important because you're showing it lots of examples where you have the lattice and then you flip the cluster and you have the next lattice. And so but in the point of normalizing flows, which we started the workshop talking about, you don't get to see how the Markov chain Monte Carlo does its work. You just start from this totally non-informative distribution and you have to somehow discover this map. And so the thing that I'm really wondering is if I, as a theorist, know that clusters are somehow very important and yet I want to build this normalizing map, how do I build into my neural network architecture that the clusters are really important and that you should be looking for clusters without having to go through this step of trying to figure out how to do some kind of RNN or something like that, some kind of model where you have the neural networks trying to investigate how MCMC does its job and look under the hood. And so to me, that's the really interesting question, because here's an example, like Rich is saying, we don't know that we'll ever find anything like a cluster algorithm for QCD, but here's an example where we really have a cluster model. And so we can really try to figure out how efficiently the machine learning can discover the cluster algorithm without having been given lots of hints as to what to look for. So.
If I may come in now. So we also have 3 short presentations in this session.
Oh yeah, sure. Okay, so I can stop sharing my screen.
So thank Lena for the talk and discussion.
Yeah, thank you very much for these very great questions.
Yeah, thanks.
Okay.
It was really wonderful talk.
Thank you.